Welcome! In this session, we're diving into an intriguing problem titled, People whose list of favorite companies is not a subset of another list. We'll explore how to identify individuals whose favorite companies are unique and not subsets of anyone else's list. Get ready to uncover some exciting approaches to solve this. In this problem, we are tasked with analyzing the list of favorite companies for a group of people. Each person has their own list, and we need to determine which people have a list that is not a subset of someone else's list. A subset here means that all the companies in one person's list are also found in another person's list. The goal is to return the indices of such people whose lists are unique in this way, and the indices should be sorted in ascending order. For the input, we are given an array favorite companies, where each element represents one person's list of favorite companies. The constraints specify that we can have up to 100 people, and each person can list up to 500 unique companies. Each company name is a string of lowercase English letters with a maximum length of 20 characters. For the output, we need to provide the indices of people whose lists are not subsets of any other lists, sorted in ascending order. Let's consider an example to understand the problem better. Suppose the input is a list of favorite companies for 5 people. Person 0 has the list, LeetCode, Google, Facebook. Person 1 has, Google, Microsoft. Person 2 has, Google, Facebook. Person 3 has, Google, and person 4 has, Amazon. The output for this example is 0, 1, 4. To understand why, let's examine each person's list. For person 0, their list contains LeetCode, Google, and Facebook, and no other person's list contains all 3 of these companies, so this list is not a subset of anyone else's. Similarly, person 1's list contains Google and Microsoft, and no one else has both of these companies in their list, so person 1 is also included in the output. Continuing with the example, we examine the remaining people. Person 2's list is Google, Facebook. This list is a subset of person 0's list, because all the companies in person 2's list are also found in person 0's list. Therefore, person 2 is excluded from the output. For person 3, their list is Google. This list is a subset of both person 0's and person 2's lists, so person 3 is also excluded. Lastly, person 4's list is Amazon. No one else has Amazon in their list, so person 4 is included in the output. Thus, the final result for this input is 0, 1, 4. Now let's look at another example. Suppose we have the following input, person 0's list is A, B, C, person 1's list is A, B, person 2's list is B, C, person 3's list is A, and person 4's list is C. The output in this case is 0. Here's why, person 0's list is A, B, C, and no other person's list contains all 3 of these companies, so person 0 is included. Person 1's list is A, B, which is a subset of person 0's list, so person 1 is excluded. Similarly, person 2's list, B, C, is also a subset of person 0's list, so person 2 is excluded. Person 3's list, A, is a subset of person 1's list, so person 3 is excluded as well. Finally, person 4's list, C, is a subset of person 2's list, so person 4 is excluded. Therefore, the output is 0, as only person 0's list is not a subset of another. Finally, let's examine one more example with simpler input. Suppose we have 3 people, and their lists are A, B, and C. In this case, the output is 0, 1, 2. Each person's list contains only one company, and no 2 lists share the same company. Since none of these lists is a subset of any other, all 3 indices are included in the output. To summarize, the problem involves checking subset relationships between lists, and the constraints ensure that lists are not empty and contain unique company names. Edge cases include situations like having only one person, where their index is always included, or cases where all lists are identical, resulting in an empty output. By carefully comparing each person's list with every other list, we can determine the correct result efficiently while adhering to the constraints. To begin, let's analyze the approaches we can consider for solving this problem. The first and most straightforward method is the brute force approach. The intuition here is simple. For each person, we compare their list of favorite companies with every other person's list to see if it's a subset. If it is, we exclude that person from the result. While this method is easy to conceptualize and implement, it involves nested loops where, for each person, we compare them with every other person. Since subset checking between two lists takes time proportional to the size of the larger list, the total time complexity becomes O, n squared asterisk m, where n is the number of people and m is the average list size. The space complexity, however, is low at O, 1, as it doesn't require any additional data structures. Despite its simplicity, the brute force approach is inefficient for larger inputs due to the high number of comparisons and the lack of any optimization, making it impractical in many scenarios. To address these inefficiencies, we can turn to our second approach, which involves using hash sets for faster subset checks. Now, let's consider the optimized approach that uses hash sets. The key idea here is to convert each person's list of favorite companies into a hash set. This allows us to take advantage of the isubset operation, which is faster than comparing lists element by element. With this optimization, we iterate through the people and compare their hash sets in pairs. For each person, we check whether their set is a subset of another person's set. If it is, we exclude them from the result. While the subset check still takes time, hash sets make this operation more efficient in practice. The overall time complexity remains O, n squared asterisk m in the worst case because we're still comparing all pairs, but practical performance improves significantly due to the faster operations. The space complexity increases to O, n asterisk m, since we're storing the hash sets. This approach strikes a balance between ease of implementation and improved runtime, but it still involves quadratic comparisons, which might not be ideal for very large inputs. To further reduce redundant comparisons, we consider a third approach that introduces sorting. Building on the hash set optimization, the next approach incorporates sorting to avoid unnecessary pairwise comparisons. By sorting the lists of favorite companies based on their size, we can process smaller lists first, which are less likely to be subsets of multiple larger lists. This reduces the number of comparisons we need to make. The steps are straightforward. First, pair each list with its index and sort the pairs by list size. Then, as we iterate through the sorted lists, we use hash sets to perform subset checks only with larger lists that come later in the order. Sorting introduces an O, n log n, pre-processing step, but it pays off by significantly reducing redundant comparisons during the subset checks. The overall time complexity is O, n log n plus n squared times m in the worst case, though the reduction in comparisons means the average case can perform much better. The space complexity remains O, n asterisk m, due to the use of hash sets. This approach is particularly efficient when the input lists vary significantly in size, as sorting helps us focus on the most meaningful comparisons. With this in mind, we can now determine the most suitable strategy for this problem. After evaluating the options, we've chosen the optimized approach with sorting as the final strategy. This method strikes a balance between clarity, efficiency, and scalability. By sorting the lists of favorite companies by size, we ensure that comparisons are focused on the most relevant cases, avoiding unnecessary work. The use of hash sets further enhances performance by making subset checks faster, even for larger lists. The key insights that make this approach effective include the realization that sorting naturally reduces the number of comparisons, and hash sets provide an efficient way to check subset relationships. While the brute force method is too slow for larger inputs, and the hash set approach still involves all pair comparisons, sorting minimizes redundant checks and is more efficient for diverse input sizes. Although sorting introduces pre-processing overhead and hash sets require additional space, these trade-offs are justified by the improved runtime performance and scalability. This combination of techniques ensures that the solution is both practical and efficient, even for larger datasets, making it the preferred approach for this problem. To solve this problem, we start by converting each person's list of favorite companies into a set. This is because working with sets allows us to easily and efficiently perform subset checks. For example, if the input favorite companies is A, B, B, C, A, we transform it into a list of sets A, B, B, C, A. Once we have the sets, we use a nested comparison approach. In the outer loop, we assume that the current person's set is not a subset of any other. Then, in the inner loop, we compare this set against every other person's set. If we find that the current set is indeed a subset of another, we mark the person as excluded and stop further comparisons for them. This ensures that we skip unnecessary checks and focus only on identifying those whose lists are not subsets of any other. After completing the nested comparison process, we compile the indices of all people whose sets were not flagged as subsets. For our earlier example with A, B, B, C, A, the sets corresponding to indices 0 and 1 are not subsets of any other, so we return 0, 1. There are several key insights at play here. First, subset operations using sets are significantly more efficient than comparing lists. The average time complexity for a subset check is proportional to the smaller of the two sets being compared, which is much faster than comparing entire lists element by element. Second, the algorithm avoids redundant comparisons by breaking out of the inner loop as soon as we determine that a person's list is a subset. Finally, we account for edge cases. If there's only one person, their list can never be a subset, so we return 0. Similarly, for people with identical lists, only one of them is included in the result. To implement this algorithm efficiently, we rely on two key data structures. The first is sets, which are chosen because they support fast and optimized subset operations in most programming languages. For example, the isubset method in Python provides an intuitive and efficient way to check if one set is contained within another. The second data structure is Boolean flags, which we use to track whether a person's list has been marked as a subset. This prevents us from mistakenly adding excluded indices to the final result. In terms of complexity, the time complexity is driven by the nested loops. The outer loop runs for each person, and the inner loop compares the current person's set to all others. Each subset check has a cost proportional to the smaller of the two sets being compared. Overall, the time complexity is O, n squared asterisk k, where n is the number of people and k is the average size of a list. The space complexity is O, n asterisk k, as we store the sets in memory. Here's how the algorithm can be implemented in pseudocode. First, we convert the input favorite companies into a list of sets. Then, we initialize an empty list called result to store the indices of people whose lists are not subsets. For each person, we assume their list is not a subset by default. We then iterate through all other people and check if the current person's set is a subset of another person's set using the isubset method. If it is, we mark the person as excluded and stop further comparisons for them. If no such subset relationship is found, we append the person's index to the result list. Finally, we return the indices stored in result. This approach balances clarity and efficiency, leveraging the strengths of sets and early exits to achieve our goal. The output for our example input is 0, 1. This means that the favorite company lists for the people at indices 0 and 1 are not subsets of any other person's list. By following this structured approach, we ensure that the algorithm efficiently identifies the desired indices while handling edge cases and optimizing for performance. The combination of set operations, nested comparisons, and early exits makes this solution both clear and robust. This Python solution is for LeetCode problem number 1452, people whose list of favorite companies is not a subset of another list. The goal is to identify which people's favorite company lists are not subsets of any other person's list. Explanation. 1. Convert lists to sets. The favorite company's input is a list of lists. Since checking subsets is more efficient with sets, we first convert each person's list into a set using a list comprehension. The favorite sets list stores these converted sets. 2. Outer loop, person I, we loop over each person I. For each person, we will determine if their list of favorite companies is a subset of any other person's list. 3. Inner loop, comparison with person J. For each outer loop iteration, we compare person I against every other person J. If I and J are not the same person, I equals J, we check if the set of person I, favorite sets, I, is a subset of person J's set, favorite sets, J, using the isubset method. For subset check, if we find that favorite sets, I, is a subset of favorite sets, J, we mark his subset as true and break out of the inner loop, as we no longer need to compare person I with other people. 5. Add to result. After checking all other people, if his subset remains false, it means person I's list is not a subset of anyone else's, so we add their index I to the result list. 6. Return result. Finally, we return the result list, which contains the indices of the people whose favorite company lists are not subsets of any other person's list. Complexity. Time complexity. The solution involves two nested loops, leading to O, n squared, iterations, where n is the number of people. Each subset check is O, K, where K is the average size of the lists. Overall, the complexity is O, n squared asterisk K. Space complexity, the space used for the favorite sets list is O, n asterisk K. This solution efficiently handles the problem requirements and edge cases, such as duplicate companies in a person's list or empty lists in the input. Here, we start with the Java implementation of the solution. First, we import the necessary packages, including java.util*, which provides the collections framework we'll use. In the people indexes method, we take a list of lists called favorite companies, where each inner list represents a person's favorite companies. The first step is to determine the number of people, n, and then convert each person's list of favorite companies into a set. This conversion to sets is done using a loop that iterates over favorite companies and creates a hash set for each person's list. By using sets, we can efficiently check for subset relationships later. Next, we initialize an empty list called result to store the indices of people whose favorite company lists are not subsets of any other person's list. With this setup, we begin the main logic to compare each person's list against every other person's list. For each person I, we initialize a flag is subset as false. We then use another loop to compare IS list with every other person's list, represented by index j. The conditions inside the if statement ensure that we only check subsets when I and j are not the same. The size of IS set is less than or equal to JS set, and JS set contains all elements of IS set. If these conditions are met, is subset is set to true, and we break out of the inner loop, as we already know IS list is a subset. Once the inner loop finishes, if is subset remains false, we add I to the result list because their list is not a subset of anyone else's. Finally, we return the result list, which contains the indices of all such people. To solve the problem, we start with example 1, which has 3 lists of favorite companies. The goal is to determine which person's list is not a subset of any other. First, we convert each person's list into a set for better performance during subset checks. Here, favorite sets becomes a list of sets, Google, Facebook, Google, and Google, Facebook, Amazon. Next, we use 2 loops to compare each person's set, I, with every other person's set, j. For the first person, I equals 0, their set is Google, Facebook. Initially, we assume it is not a subset of any other set by setting is subset to false. Then, we begin comparing it to other sets using an inner loop. The first comparison is with j equals 1, which is the set, Google. Since Google, Facebook, is not a subset of Google, the check returns false and we proceed to the next comparison. Now, for the same person, I equals 0, we compare their set, Google, Facebook, with j equals 2, which is the set, Google, Facebook, Amazon. In this case, Google, Facebook, is indeed a subset of Google, Facebook, Amazon, so is subset is set to true, and we stop further comparisons for this person. Since their list is a subset of another, they are excluded from the result. We then move on to the next person, I equals 1, whose set is Google. This set is compared with both j equals 0 and j equals 2. In both cases, Google is a subset of the other sets, so this person is also skipped. Finally, for I equals 2, the set Google, Facebook, Amazon is compared with the others. It is not a subset of any other set, so we add their index, 2, to the result. The output for this example is 2, meaning only the third person's list is not a subset of another. In example 2, we have 3 lists of favorite companies where each list contains only one unique company. After converting the lists to sets, favorite sets becomes Google, Facebook, and Amazon. This time, each person's set is compared with all others, but since every set contains a unique company, no set is a subset of another. As a result, all indices, 0, 1, and 2, are added to the result. The output here is 0, 1, 2, indicating that all 3 lists are unique in the sense that none is a subset of another. In example 3, we have a more complex scenario with overlapping subsets. The input lists are converted to sets, resulting in A, B, B, C, A, B, C, A, and C. For the first person, I equals 0, their set, A, B, is found to be a subset of A, B, C at index 2, so they are skipped. Similarly, for the second person, I equals 1, their set, B, C, is also a subset of A, B, C, so they are skipped as well. Next, for I equals 2, the set A, B, C is not a subset of any other set, so index 2 is added to the result. For I equals 3, the set A is also unique and not a subset of any other, so index 3 is added. Finally, for I equals 4, the set C is similarly unique, so index 4 is added to the result. The output for this example is 2, 3, 4. This highlights how the algorithm systematically identifies indices of people whose favorite company's list is not a subset of any other. By converting lists to sets and using efficient subset checks, we achieve a time complexity of O n superscript 2, where n is the number of lists. This ensures the algorithm is both clear and efficient for solving the problem. To analyze the time complexity of this solution, we start by converting each person's list of favorite companies into a set. This step is necessary because set operations like checking for subsets are more efficient than working with lists. If each list has an average of m companies and there are n people, converting one list to a set takes O, m, so converting all lists requires O, n asterisk m. Next, we move to the subset checking step, where we determine if a person's list is a subset of another person's list. For each individual, we compare their set to the sets of all other individuals. Each subset check involves comparing the smaller of the two sets and, in the worst case, takes O, m and time. Since every person compares their set with the sets of n1 others, we perform O, n squared, comparisons in total. Multiplying this by the O, m, cost of each comparison, the subset checking step has a time complexity of O, n squared asterisk m. Combining these two steps, the overall time complexity of the solution is dominated by the subset checking, resulting in O, n squared asterisk m. Now, let's look at the space complexity. The primary contributor to space usage is the conversion of lists into sets. Each set requires O, m, space to store the companies for one person, and with n people, this results in a total space requirement of O, n asterisk m. Additionally, we store the indices of people whose lists are not subsets in a result list. In the worst case, all n indices are stored, which adds O, n, space. Temporary variables, such as those used for loop counters or flags like isSubset, require only constant space, or O, 1. Therefore, the overall space complexity is dominated by the storage of the sets, which is O, n asterisk m. This balance of time and space efficiency allows the solution to scale better than brute force methods, which we'll discuss shortly. Let's break down the best, average, and worst-case scenarios for this algorithm. In the best case, every list of favorite companies is unique, and no subset checks succeed. While this might allow the subset checks to terminate early in some cases, the algorithm still performs O, n squared, comparisons overall, and each comparison costs up to O, m. Thus, even in the best case, the time complexity remains O, n squared asterisk m. In the average case, the input is processed similarly to the worst case. Subset checks are still performed for most comparisons, and the overall complexity does not improve significantly. Finally, in the worst case, all lists are similar in size, and subset checks involve comparing nearly all elements in each set. This results in O, n squared, comparisons, with each comparison taking O, m. As a result, the time complexity for the worst case is also O, n squared asterisk m. To understand the efficiency of this solution, let's compare it to a naive brute force approach. A naive method might involve directly comparing lists without converting them into sets. In such a case, a single subset check would require O, m squared, time, as each element in one list would need to be compared to all elements in the other list. This would lead to an overall time complexity of O, n squared asterisk m squared, which is significantly worse than the O, n squared asterisk m, achieved by using sets. By leveraging set operations, the current solution optimizes subset checks to O, m, per comparison. However, there may still be opportunities to further optimize the algorithm. For example, sorting the lists or using hash maps to pre-process data could help reduce the number of subset checks or the cost per check. Finally, the big O complexity can be confirmed mathematically. With nested loops iterating O, n squared, times in each subset check taking O, m, the overall complexity is dominated by the O, n squared asterisk m, term, consistent with our earlier analysis. One common pitfall when solving this problem is overlooking edge cases. For instance, what happens if the favorite companies list is empty or if all individuals share the exact same list of companies? These scenarios might not be immediately obvious but can lead to runtime errors or incorrect results if not handled properly. It's important because addressing edge cases demonstrates thorough problem-solving skills, something interviewers value highly. Another mistake is using inefficient subset checks. Manually comparing lists with nested loops can significantly increase the time complexity. Instead, converting lists into sets enables quick subset checks in constant time for each comparison, making your solution much faster. Finally, failing to sort or pre-process the input can also lead to inconsistencies or redundant comparisons. By sorting the favorite company's lists or working with sets, you ensure uniformity and avoid subtle bugs that could derail your solution. Another frequent issue is misunderstanding the problem statement itself. For example, some might mistakenly return the indices of lists that are subsets of others, rather than those that are not. This leads to completely wrong outputs, even if the implementation is otherwise efficient. It's crucial to carefully interpret what the problem is asking for. Over-reliance on brute force is another challenge. While a naive O(n)² approach may work for small inputs, it won't scale well with larger constraints, such as when the number of people is in the tens of thousands. To excel in interviews, it's vital to transition to optimized techniques like hashing, sorting, or even bitwise operations. Remember, set operations are particularly useful here. Understanding how to use subset and superset methods in Python or their equivalents in other languages can dramatically improve efficiency. Also, be ready to discuss trade-offs between brute force and optimized solutions. For example, brute force might work for small test cases, but it's crucial to highlight why it would fail for larger ones. Lastly, always test your solution thoroughly. Use diverse test cases, such as single-element lists, duplicate lists, or completely disjoint lists, to ensure your code handles all scenarios effectively. This problem also shares similarities with other LeetCode problems that can help you build relevant skills. For instance, LeetCode 128, longest consecutive sequence, involves leveraging set-based approaches for efficient lookups. Another related problem is LeetCode 90, subsets 2, which focuses on generating subsets while avoiding duplicates. LeetCode 187, repeated DNA sequences, demonstrates the power of hashing for detecting duplicates efficiently. And finally, LeetCode 49, group anagrams, highlights the importance of pre-processing data into a canonical form, such as sorting strings, to simplify comparisons. Now, discussing alternative approaches, a brute force method involves directly comparing every pair of lists to check if one is a subset of the other. While simple to implement, it has a high time complexity of O(n)²(m), where n is the number of people and m is the average size of the lists. This approach is fine for small inputs but becomes impractical for larger datasets. A better option is set-based optimization. By converting lists into sets, you can leverage efficient set operations like subset and superset checks. This reduces the time complexity to O(n)², as each subset check is constant time. While still quadratic, this method is much faster than brute force for larger inputs. Another alternative is sorting the favorite company's lists and then filtering out non-unique ones by iterating through them. The sorting step, which dominates the time complexity, takes O(n)(m)log m, and the overall complexity becomes O(n)² due to pairwise comparisons. This method strikes a balance between simplicity and performance but may still be slow for very large inputs. A more advanced approach involves using a tree. By inserting each list into a tree structure, you can represent the lists hierarchically. Traversing the tree allows you to efficiently identify lists that are not subsets of others. This method has a linear time complexity of O(n)(m) for both insertion and traversal, making it highly efficient for large inputs. However, it comes with added implementation complexity. While not always necessary in an interview setting, the tree-based approach is worth knowing as it highlights a deeper understanding of data structures and their applications. Thanks for sticking with us. We've covered the main ideas of solving this problem, from brute force to optimization strategies. Remember, practice makes perfect. Be sure to tackle similar problems to refine your skills. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!